So when we were evaluating, as we did a little while ago, compound interest, which is a function of exponential growth, we can also have exponential decay. And the difference is whether the rate is positive or negative. And so if it is a situation where we've got exponential decay, our rate is going to be declining or less than zero. I should say really less than zero. And if it's exponential growth, our rate is going to be greater than zero. So let's look at this particular problem. We're asked to calculate this a couple of ways, both with an annual decline and a continuous decline. So we got a population of a town is declining at a rate of 6%. And of course, our rate here then is going to be negative 0.6. If the current population, and that's going to be our P, if you will, in our two formulas, 12,426, predict the population in 5 and 10 years using each model. So we're asked to use an annual model and a continuous model. So our annual model, our formula would be, again, A, the account value or the amount, is equal to P, the starting point, and we could say N there, 1 plus the rate, and of course in this case it's negative, and that's really over N, but when we're dealing with annual, that's just 1, so we can just ignore that. Raised to the power of N, again, this is 1, well, and times the time. And again, in our model here, since we're doing annual, N is just going to equal 1. And then our continuous model is we got A equals, and that's the amount, P, our starting point, and I might see that written as N subscript O or something. Let's see, and then E, natural base raised to the power of the rate times the time. So again, we've got a negative rate of 0, and that should be, correct that, 0.066%, negative 0.06 rate of decline. So let's jump over to the calculator, and we're going to do these both annually and continuously, starting with a town that has a population currently of 12,426, and we're trying to predict where they'll be based on this declining growth rate, or actually rate of decay, maybe another way of saying that, of the population of this town. All right, well, let's make some predictions based on these. We got this town. It's got a population of 12,000, what was it, 426 currently. And if we had an annual rate of decay, we would have 1 minus 0.06. And if we're going to make this prediction, let's do it first 5 years out. So we're going to raise this to the power of 5. What do we expect the population of this town to be in 5 years with an annual rate of decay of 6%? And let's see, that would be 9,119 people. Well, how about in 10 years, what do we expect? So I got 12,426 times 1 minus the 6% rate of decay, or minus 0.06. Let's close our parentheses here. And now we're going to raise this to the power of 10 for 10 years. And where do we expect this town to be 10 years later? Well, it's lost about half its population, hadn't it? We would say that would be 6,693 if I rounded that up, since it's 0.8. Well, how about if we got a continuous rate of decay? Let's see, again, we start with 12,426, current population of the town. Then we're going to use the natural base, so I'm going to hit second. ln, or e to the x, and then we've got a negative 0.06 rate of decay. We're first going to do it times 5 years. And so if we had a continuous rate of decay, what would our population be in 5 years? Well, about 9,205 people. And what about if we took that out 10 years? 12,426 again. Natural base. Raised, it's still got the same negative 0.06 rate of decay. But this time we got that times 10 for 10 years. And so in 10 years, we would predict that this would be 6,820. Now notice how the continuous rate of decay actually gives us a little bit higher values than the annual rate does. And I would expect to see the opposite occur if this was a growth rate, but in a rate of decay, actually we see less of a decline than what we do with an annual rate of decay. That's interesting.